We have to do some computations to get to the answer of this. And these computations are coming here, and you can see the test we'll be doing will come up next. Let's see how it goes. First, I repeat the model. And I hope you see the resemblance to a linear regression model in many ways. Many things are actually working the same way. It's not exactly the same, but there are similarities. And that takes us to actually being able to realize that the variability in such data can actually be split into those two terms. And let me actually to look at this. The total variability, and then I'll go a bit back and forward now here because I have the formulas here. This is the total variability. We need a kind of annoying double notation, double summation, because I indexed my observations with I and j. But really, if you look at this, this is just summing across all the observations, all the 12 of them in my toy example, and comparing each individual observation with the mean. I hope you recognize that type of computation as what we would do if we would begin to just compute the variance of all the y's in a big pool of chunk of data without thinking about which group they come from. Just take all the y data, put them in a pool and compute the variance. Don't divide by something, just compute the sum of squares before dividing by anything. That's what we call the total variability now. That's just the raw variability of the data, ignoring the group structure. We could also, I'm gonna jump back now, maybe I should actually see if it works for me to, in between these two, I could see if I could do this, because I could use this plot again. Good. Because what's the total variability? Let me just, I don't remember the numbers actually. Maybe I should check. No, I'm just, what's the mean of these data? Total mean, something around here. Right? Then I could take each individual data point, compare with the mean, right? Like this. That's my total variability. Like that, right? The next thing is to think about quantifying the differences between the means. So that's y1, y2 bar, y3 bar. And then somewhere here again I have the overall mean. Then I could take each of those three individual means, group means, and compare and measure how different are they from the overall mean. This is an expression of how different are the groups really. How different are the group means really. This is what I would call this one. That gives me the SS treatment, the sum of squares of treatment groups. That's the TR, this treatment terminology. That's a historic terminology used by Fisher that created these tools. And that's this term. And the formula for that term came last. The formula, and that's really actually the core measure here, because this is the measure that aims at the core purpose of this analysis, to find out whether these means are really different from each other or not. So some sort of measure of how different means are. Please think about when we had only two groups. How did we construct a test statistic to measure the difference between two groups, the t-statistic? Well, we took one mean, we took the other mean, we subtracted them from each other, and then we divided by some variant stuff to get the t-statistic. Now the problem of having k means, k could be 8, 3, 12, 15, 100, is that there is no single way to just take two means and subtract them from each other. So with multiple means, we need a different way to compare means with each other. And the general principle of comparing more than two means with each other is by means of computing a variability. And that's why analysis of variance is called analysis of variance, because we compute a variance measure to express mean differences. And that's why it's called analysis of variance, because it's the variability from mean to mean that helps us answering the question. And that's what we express formally here. We take the individual group means and compare with the overall mean. We remember how many observations in each group, and that could be different from group to group. That's not a problem at all. It's part of the computational theory that we could easily handle 3, 12, and 100 in each group. That's perfectly doable. And that was what I visualized in here. That was the SSTR. Anyway, now I removed a lot of stuff we didn't see. Finally, we need to think about when we are going to compare these three group means with each other. And that's the purpose of everything. I've repeated myself. We need to consider within group variability. SSTR, that's like the between group variability, the between group difference. What would the between group variability be if all three group means are equal? It would be 0, because that thought case would be here, here, and here. And how would they differ from their own mean? By 0, right? So a measure of 0 means, obviously, it's just good to have that on your backbone. That tells us there's no difference at all. Of course, due to randomness, exact 0 will never be seen in real data. But we need to think about the noise within each group. Or you could say an attempt of estimating the sigma, the within group variability. That is expressed by the red. And if we take all the red ones, we get the SSE. I believe this is my notation, otherwise, yeah, good. That was the SSE, and formula-wise it came here. It takes each individual observation and compare it with sort of within the group. So we just compared how close to the group mean is the individual observation. So it's measuring the fluctuation, the noise, the residual, the within group variability. It's not measuring group differences, but it's measuring the noise within groups. That's a good thing, because we can use that as a kind of way to evaluate the other one. The actual interesting measure, which is here, that expresses how different are the groups, is going to be compared with the variability within groups, because the difference between groups would have to be larger than what we would expect from the noise level, the variability from within groups. That's the idea of it. And to go back to the overall formula, it turns out, even though that I talked about 3 variations here, the total variability, the between group mean variability, and the within group variability, which we average across the group, so it's kind of a pooled between group, within group variability. There are only 2 ones, because the between plus the within actually gives the total. It's kind of Pythagorean result kind of way here, that there is nothing more going on than the between and the within. The total variability is the sum of those 2. May seem obvious, and it is in a way, but it's also a mathematical fact. When we talk about one-way ANOVA today and then two-way ANOVA next time, it's because we have this thing that one-way refers to the fact that I only have one way of categorizing or factorizing or grouping my situation. And I already told you that why we use this funny name, because it's really comparing means by computing the variability between group means. That's the way we compare the means. Then the way most softwares in the world work for you is in this way. It gives you the summary of all of these computations that I just told you. It gives you the sums of squares. Basically, these were the 3 ones I gave you explicit formulas for. The ANOVA table, as it comes out of R, when you do like this, you have to use the same kind of model notation, LM, linear model, the same as the last couple of weeks. And then we have this y tilde x notation. But today x is not x. Today x is a grouping information. So we need a column in our data set, in our data frame, that sort of codes for the treatment groups, or any kind of groups. The generic name used is treatment groups. If we do that, R will spit out such an ANOVA function, at least if we ask R to do it. There is several ANOVA functions in R. Here's one of them. And then it will tell us degree of freedom, sum of squares. Basically, that's the only one I told you so far. Look at the R output. R output actually skips the total because we don't really need the total for the analysis that we do. But up here, we just give it. This is the table in mathematical terms. What we do now is to basically extract everything from these 2 sums of squares, also given by R. When we have these 2 sums of squares, and I've told you between sum of squares, within sum of squares, we have everything. We mean them, or that is, we divide the treatment sum of squares by number of treatments minus 1. It's a bit like this computing a variance across treatments, right? When we compute a variance, we divide by n minus 1. Now it's across the k groups, so we divide by k minus 1. And the mathematical theory would prove to us that that would be the right way of doing it. The residual sum of squares is being divided by n minus the number of groups. Well, that totally matches what I taught you previously, actually, and we have a bit of extra detail on that later, but basically that corresponds to, we did n minus 1 in the beginning, then we did n minus 2 in the simple regression, we did n minus p in the n minus p minus 1 in the p-dimensional MLR, and this completely matches the same line of thinking. With k groups, I divide by n minus k. That gives me the mean squares, and then the f-test statistic. And now I think I'm ahead of myself, but here it is. Anyway, these 2 divided by each other is the measure of whether groups are different or not. And even the R output would give the p-value. So even before I taught you this, what do you think the result will be in this case? Are the groups different here? You think? Yes, they are, because the null was that they were the same, and we reject the null. Actually, I'm all 1 point ahead of myself, but we know how to read p-values by now, so we have rejected a hypothesis here, and I already told you what the hypothesis was, even though I didn't really say much. And the f-value is nothing more than these 2 mean squares divided by each other, right? So it's pretty simple in the table. As long as you have the sum of squares, it's just dividing things by each other. And then at the end of it, you look up some p-value from the right f distribution. We'll get to that in a sec. That's basically the ANOVA table. I don't think I will actually do this. I think instead I will, because that's the last part. What covers this? Actually, we cover in our game. Ah, I got you there. This was a trick question, but nevertheless a pretty fair trick question at this point. To make you think about the two variances, and 20 red ones of you made the wrong choice compared to this. Let's have a look at the image. I asked you about which one had the largest residual error. That's the within group error. Maybe we need to adjust to the terminology, of course, also here. If I look at these two plots, it's of course difficult to be exact, but my options were clearly larger for the A. No, it's not, because what I'm comparing is the average fluctuation within the group. I'm not asking about what we see on group, the A data set. The A data set clearly has a larger SSTR, the between group variability, is clearly larger for the A data set, right? The groups are more different in the A case than in the B case, but the level of fluctuation within the group, like the range of these point patterns, right? If I take the three ranges in A data set and the three ranges in B data set, they are roughly the same size. They are not mathematically exact, but they are simulated from some distributions with exactly the same error. And I even picked one where it looked nice. It could be much more different than that due to randomness. So that was a good learning issue to remember to distinguish between group variability and within group variability. We had new guys on the top. I will, as mentioned, skip this part, which is about, or should we just take 2 minutes actually and see if we can do this in R and have some more learning out of that related to the same issue. Let's see. Let's see. That's all old stuff. Here we are. So this is another sort of situation where we compare two, actually quite similar to my example, right? The left one here is one with clearly group differences, and the right one is not so clear. What about the total variability? It's much larger in the first case than in the second case. How about the residual variability? It's actually similar size, but even slightly smaller in the first case than in the second case. And look at that it's pretty simple to do those computations by R. These means you can do them simply by some sums, or you can use the t-apply, or there's even anyway, it's an example illustrating exactly the same issue as we were gaming about. So